Hi there! In the previous video you saw the meaning of a confidence interval, along with an example where you saw how you could construct one. In that case the xi had a normal distribution, leading to the standardized sample mean having a student t distribution. You also saw that the central limit theorem gave an approximate confidence interval, as long as you had enough observations. Now we are going to tackle a different, non-normal example, where we can use the technique of pivotal quantities to come up with a confidence interval. Okay, let's talk particle physics. As you may know, atoms have a nucleus with protons and neutrons inside it, surrounded by an electron cloud. In some reactions, such as the ones in a nuclear reactor, free neutrons are released. In this diagram you see how enriched uranium decays into krypton and barium, and some free neutrons. These free neutrons are what we are interested in. They are no longer part of a nucleus, and as such they are not stable. After a certain time they decay into a proton, an electron and an antineutrino. After a certain time, well, actually after quite an uncertain time. On average this happens about after 15 minutes, but the time between the release of the neutron and its decay is random. This time can be very well modeled by an exponential random variable. This assertion is based on theoretical grounds. We know how the decay mechanism works, and lab experiments confirm this exponential behavior very well. So, let's consider 10 of these neutrons that have just been released. And we denote by xi the time until they decay, measured in minutes. These xi are independent, and they all have the same exponential distribution with an unknown parameter lambda. As you may recall from probability theory, the inverse of this parameter lambda is the expectation of the decay time. 2 weeks ago we saw how we can find point estimators for lambda, either by the method of moments or by the maximum likelihood method. They happen to give the exact same estimators, by the way. But now we are looking for a confidence interval. So let's see if we can find a pivotal quantity. Let's consider the sum of the xi, and let's call it S for sum. But what is its distribution? Well, the sum of n independent random variables, all exponentially distributed with parameter lambda, follows a gamma distribution, with parameters n and 1 divided by lambda. You may not be familiar with this distribution yet, so let's see what its density function is. Here it is. It looks like quite a heavy formula. But you can check that for n equals 1 we do find the density function of the exponential distribution. And that makes sense, right? The sum of one exponential random variable is exactly that exponential random variable. For n greater than 1, we basically need to multiply this exponential by a power of x. All the rest are just normalization constants. Now, don't worry how to obtain this density function, that is outside the scope of this course. Okay, so we now know the distribution of our sum S. What do you think? Can we use this S as a pivotal quantity yet? No. A pivotal quantity should have a distribution that does not depend on unknown parameters, whereas here this gamma distribution still has the unknown lambda in the parameters. However, this gamma distribution has a very nice scaling property. When you multiply a gamma random variable by a constant, this gives again a gamma random variable with still the same first parameter, but the second parameter gets multiplied by this same constant. By the way, this property actually follows from a similar scaling property for the individual exponential distributions. In our case, it means that lambda times s has a gamma distribution with parameters n and 1. And there we have it. This lambda times s is a pivotal quantity, because indeed this random variable depends on the unknown parameter lambda, and it depends on the sum of the observations, but its distribution does not depend on any unknown parameter. This is what the density function of t looks like for our case n equals 10. By the way, this is not a topic here, but do admire the central limit theorem at work. Each xi has an exponential distribution, but the sum of 10 independent xi has a distribution that is more or less bell-shaped. You can still see some asymmetry, but with only 10 random variables, that is to be expected. Okay, from now on we can proceed as before. We indicate the two values for which 95% of the area is between these values, and 2.5% is in either of the two tails. These quantiles can easily be found in R using the qgamma command. They turn out to be 4.80 and 17.08. So we get this probability expression, very similar to what we had in the previous video. Again, we want to have our unknown parameter lambda in the middle of the inequalities, so we divide the three expressions by s. In this way, we end up with a formula for the 95% confidence interval for lambda. The bounds are given by these gamma quantiles, each divided by the sum of the observations. Notice that this interval does contain the point estimator, which is 10 divided by the sum that we found 2 weeks ago. It is not symmetrical around this value, though, which was the case in other examples. This asymmetry should not come as a surprise. After all, the exponential distribution is not symmetrical, and neither is the sum of exponential distributions. Before we look at our data, let's generalize this. If we are dealing with n observations rather than 10, we will of course be dealing with a gamma distributions with parameter n and 1. And if we need any other confidence level 1 minus alpha rather than 95%, we need the corresponding quantiles. Hence, in general, we find this formula, where q n alpha divided by 2 and q n 1 minus alpha divided by 2 are the quantiles of this gamma distribution. Let's go back to the 95% and take a look at our data. Here you have the decay time of 10 neutrons in minutes. Now I have to admit these decay times were simulated using R. It is not that easy to just make a small number of neutrons. If you happen to have a few spare neutrons lying on your desk, feel free to measure their decay times. Seems quite unlikely though. The parameter used for the simulation is the one from the literature, but we'll get back to that in a minute. The sum of our observations is 131.36, so this leads to a 95% confidence interval 0.0365 to 0.1301. You may wonder, would the approach using the central limit theorem have worked here? Well, not really, actually. I mean, you could do the computations. You use the observed mean and the standard deviation of the decay times, and you just construct a 95% confidence interval for the expectation mu, which is 1 divided by lambda, as we did in the previous video. And then you take the inverse of these numbers to find a confidence interval for lambda itself. However, there are some issues with this approach. First off, this technique only gives an approximate result, whereas we obtained an exact confidence interval. No approximations were made. Also, the CLT is a limiting result, whereas R n equals 10 is not very impressive, so it would not even be a good approximation. And finally, by using the technique based on the CLT, you completely disregard the known fact that the xi have an exponential distribution. Alright, let's check our results by running a simulation. Let's go through this bit of code together. We start with two counters, which are equal to 0 at the start. Then we will draw 1 million samples of 10 decay times. So the for loop indicates that we will repeat something 1 million times. Each of those times we use the rexp command to generate 10 decay times, all with the same parameter lambda equals 0.0682. Indeed, from the literature we know that the mean lifetime of a free neutron is 14.66 minutes, which corresponds to 1 divided by lambda. So the lambda value we used was 1 divided by 14.66, which is this 0.0682. We then construct our confidence interval using the expression we just obtained. The lower bound is the 0.025 quantile of our gamma distribution divided by the sum of the decay times, and the upper bound is similar, but now using the 0.975 quantile. Then we need to check whether the true value is in this interval, and we do this using an if statement. If the lower bound is greater than the true lambda value of 0.0682, then obviously the entire interval lies above this value. In that case, we increase our first counter by 1. And we perform a similar check on the upper bound. If the upper bound is less than the true value, then the entire interval lies below this value, and we increase the second counter by 1. Keep in mind that we expect 95% of the intervals to contain the true lambda value 0.0682, and we expect 5% of the intervals not to contain this value, 2.5% at each side. Well, the first counter stops at 24,924, the second one at 25,144. And both are indeed very close to the expected 2.5% of 1 million. And of course all the other intervals do contain the true value. As you can see, this number is close to 95% of 1 million. Looks like we didn't make any mistakes in our derivation. Phew. In the next video, we will take a look at the confidence interval for a proportion p. See you then.